Welcome! Today we're diving into something that's really changing the game and how we fight cancer. We're talking about an isotope, a tiny particle that has the raw power of a cannon, but, and this is the incredible part, the precision of a surgeon's scalpel. We're talking about Actinium-225.
Okay, so here's how we're going to break it all down. First, we'll cover the basics of nuclear medicine, just to get our bearings. Then we'll get into this brilliant idea called Theranostics. After that, we'll look at the unique power of alpha particles, which is key. And finally, we'll focus in on our star player, Actinium-225, how it's made, and how it's actually used to save lives.
So, first things first, let's lay the groundwork for everything we're about to discuss. What in the world is a radiopharmaceutical? I know it sounds super complicated, but the concept itself is actually pretty beautiful in its simplicity. At its heart, it's a really clever team-up. You've got your radionuclide, that's the radioactive part, the actual weapon, and then you attach that to a targeting molecule, which is basically a biological GPS that knows exactly which cells in the body to hunt for. When you put them together, you get this single agent designed to seek and destroy a disease.
So, we have this powerful two-part molecule. Now, what if you could use that same basic platform for both finding the disease and then turning around and fighting it? Well, that is the revolutionary idea behind Theranostics, which you can kind of guess from the name, is all about blending therapeutics with diagnostics.
The power here is all wrapped up in that one phrase: see what you treat and treat what you see. Just imagine for a second. You use a drug with a low-energy isotope to go in and light up every single cancer cell in the body on a scan. Then, once you've confirmed exactly where the enemy is, you just swap in a high-energy therapeutic isotope onto that very same drug and send it back in to destroy only those cells you saw. That's the incredible promise of Theranostics.
This brings us to a very specific, and I mean incredibly potent type of therapy that makes all this so promising. See, not all radiation is the same. And when it comes to killing cancer cells up close and personal, alpha particles are in a league of their own.
And this table right here illustrates the difference perfectly. Just look at those numbers. Alpha radiation packs a massive energy punch. We're talking 5 to 8 million electron volts. But then, look at its range in your body's tissues. It's less than 1/10 of a millimeter. It literally can't even get through a sheet of paper.
And this unique combination is exactly what makes it so perfect for fighting cancer. An alpha particle can completely shatter the DNA of a cancer cell it hits, but it dumps all of that destructive energy right on the spot, sparing the healthy tissue that's maybe just a few cells away. It is the ultimate targeted weapon.
So, if alpha particles are ammunition, then we need the perfect delivery system, right? The perfect weapon to fire them. And that brings us to the star of our show, the isotope that has so many people in medicine so incredibly excited, Actinium-225.
First off, its timing is just right. It has a half-life of about 10 days, and that is the sweet spot. It's long enough that you can actually produce it in a lab, attach it to a targeting molecule, ship it to a hospital, and give it to a patient, all without it losing too much of its power along the way.
But its perfect half-life is only part of the story. The truly incredible thing about Actinium-225 is what happens after it gets to the target. And get this, it's not a single shot. It's like a microscopic cluster bomb. As just one atom of Actinium-225 decays, it sets off a chain reaction, releasing a cascade of not one, but 4 separate, high-energy alpha particles. This just unleashes an immense amount of destructive power right on the cancer cell's doorstep.
Now, this all sounds absolutely fantastic, but you might be wondering, how do we get our hands on this rare and powerful isotope? And maybe more importantly, once we have it, how do we make absolutely sure it only attacks cancer cells and leaves the healthy ones alone?
Well, the production process is a serious feat of nuclear physics. Scientists start with a more common element, thorium-232. They put it inside a massive particle accelerator and then just blast it with a high-energy beam of protons. This bombardment literally knocks pieces off the thorium atoms and rearranges them, transforming them into our rare isotope, Actinium-225. It's really like a form of modern-day alchemy.
So this is it. This is the most important question of all. Having a weapon this powerful is pretty useless if you can't aim it. How does this magic bullet navigate the trillions of cells in the human body and find only the cancerous ones?
The answer is in this brilliant 3-part system. First, you have a targeting molecule. Think of it like a homing beacon that's designed to find a protein that's only found on cancer cells. Then you have the Actinium-225 payload, and holding them all together is the critical piece of the puzzle, the chelator.
This chelator is the real unsung hero here. You can think of it as a molecular cage with an unbreakable grip. Its one and only job is to lock on to that radioactive actinium atom and never let it go while it's traveling through your bloodstream. This is so critical for safety. It makes sure that the radioactive payload doesn't just break free and cause random damage. It's only unleashed precisely when the targeting molecule docks with a cancer cell.
So to put it all together, this analogy is just perfect. The cancer cell has a unique molecular lock on its surface. The targeting molecule is the key designed for that lock. The chelator attaches the radioactive payload to that key, and the result is a treatment that can unlock and destroy only the very specific cells we want it to.
You know, technologies like Actinium-225 targeted alpha therapy are no longer just science fiction. They are in clinical trials as we speak. And it really forces us to ask, what does the future of medicine look like when we can design treatments not just for a type of cancer, but for the specific molecular fingerprint of an individual patient's disease? It's a truly exciting time to be alive.